Hello everyone, welcome to the new session of the 5G Massive MIMO training. In today's session, we are going to cover the part highlighted by red here, which is related to uplink beam management. This will be covering the overview about the channel sounding for uplink beamforming, and also afterwards we'll go through the two types of the uplink transmission scheme, which is related to codebook and non-codebook based. Then we'll be ending by uplink beam management in general, how it's working in 5G. In case if you didn't watch the previous 4 sessions, which is had been covering a very important information related to the downlink beam management and also other requirements related to UE capabilities and so on, and also MIMO introduction in general about massive MIMO and many other good information. I advise you to go and watch all these 4 sessions before going to the uplink beam management part. Let's move forward to see what we have. Before going into the details of the introduction about the uplink sounding or the uplink beamforming in general, I would like first to recap the information about the sounding reference signal functions, main functions. If you remember, we have covered this part in multiple sessions, previous sessions. But in general, SRS function or sounding reference signal, which is being usually transmitted in the uplink from the UE to the GNB, and the GNB will be starting like estimating the uplink channel propagation and also downlink channel propagation based on the SRS transmission. So in general, if you remember, we have 5 functions for the SRS, which is related to the uplink channel aware scheduling and link adaptation. Usually the GNB, after estimating the channel propagation for the uplink based on the SRS transmitted from the UE, the GNB would be start like evaluating the MCS, and it can do kind of link adaptation, increasing or reducing the modulation scheme based on the channel propagation and so on. Also, it will identify how many resource blocks required for the PU SCCH in the uplink direction, in case of the uplink data transmission. Then, if you remember, also we have discussed in the previous session about that SRS can be used in terms of channel reciprocity whenever you have TDD to estimate the downlink propagation, and we have covered this in details. We have went through the information related to antenna switching capabilities and many other important information. You can refer to session 4 if you would like to go through these details. Now, the last 3 types here, or functions of the SRS, this is what we are going to cover today, which is related to 2 different uplink transmission scheme, non-codebook and codebook. Then we'll be ending by uplink beam management. Let me move forward to cover all these kind of functions for the SRS, which is more related to data transmission in the uplink, which is a PU SCCH. So let's move forward to see what we have in details. The first part I'm going to cover here from high-level perspective, it's related to the channel sounding for uplink beamforming or channel sounding for uplink data transmission in general. The standard, which is a 3GPP, defines 2 types of uplink transmission schemes. One called codebook-based, which is based on the sounding reference signal, and this is like supported by both TDD and FDD, because the codebook-based doesn't require the channel reciprocity. It can be done for both FDD and TDD, and as you know, this channel reciprocity, whenever we can use downlink for uplink estimation, downlink reference signal for uplink estimation, or channel estimation, or for example, uplink reference signal for downlink channel propagation estimation, and vice versa. And codebook usually means what? Means that you have 3GPP has defined a specific set of pre-coding weights, which can be selected and sent by the receiver to the transmitter to tell him, I would like to have for example, the transmission at this particular pre-coding matrix or whatever. We'll cover this part, which is here in more details here. So simply this one, initially the UE would be transmitting the SRS in the uplink direction. Then the GNB will be estimating the uplink channel propagation based on the sounding reference signal for different poles, as will be discussed in more details in the next slide. Then it will feed back something called TPMI. This transmit pre-coding matrix indication. This is telling him which pre-coding matrix the GNB would like the UE to transmit the data in the uplink direction through assigning this TPMI for the UE. The second type is called non-codebook-based transmission. This means what? Means that the UE will measure the downlink CSI-RS to estimate the uplink or to send a already pre-coded SRS and uplink direction to tell JGMB directly this is a pre-coded SRS transmitted. We can select any of them and send it back to me so I can use it for the PU-SCH transmission. We discussed this in important details, but the important information here you would like to know that non-codebook and uplink is mainly used for TDD because this requires channel reciprocity. And if you recall, channel reciprocity means what? Means that because TDD, which is time division duplex, is using the same frequency in the uplink and downlink, but it's just being transmitted in different timing, as you know already. So this is like based on the CSRS, and this is called non-codebook-based. Now let's move forward to see in details each of these types for the uplink transmission scheme. The first type about uplink beamforming based on codebook-based SRS. Actually, this is like one of the most important parts for the uplink, especially uplink transmission scheme. So we are going to go in details about this part related to the UE capabilities requirement, related to the practical aspects, like what kind of, from practical perspective, what kind of you need to do, how to optimize the uplink performance in general for the codebook-based SRS. So in general, codebook-based SRS, how it's work in 5G. So initially, as you can see here, I had summarized it in 4 steps, as mentioned here. So the codebook-based transmission procedures can be done like in these 4 steps. Initially, the GMB must inform the UE which type of codebook or which type of uplink transmission scheme the UE need to consider. So initially, the GMB will send RR serial configuration message in downlink direction, which this including in the RR serial configuration message something called SRS resource set with usage type codebook, telling him that we are going to use codebook to find your best beam in the uplink for the PU-SCH for the uplink data transfer. So how the GMB in the very beginning define which type is going to be used, either codebook or non-codebook, for example. The first thing that GMB need to know before this step, the UE capability. For example, some UEs are not supporting, let's say, codebook, or supporting only codebook and not supporting non-codebook. So this can be covered in the UE capability itself. So as written here, once the BTS knows the UE capability, it can instruct the UE to use either codebook-based transmission or non-codebook-based transmission using the TX config information element within the PU-CH config. Actually, this is a message you will find it within the RSCD configuration message, which is telling him under the PU-CH configuration, it will tell him, for example, the TX config, we are going to use, let's say, codebook and so on. So here it will just instruct him to tell him I'm going to use codebook. Then afterwards, what will happen once this message being sent and the RSC official message? Again, as mentioned here, the BTS configured the UE to use an SRS resource with usage codebook, for example, here, and this is under this SRS resource set can include, for example, multiple SRS resources, for example, 1 or 2. This is based on the number of antenna panels. For example, if the user have 2 antenna of the UE support 2 antenna panels, so it can use 2 different SRS resource set. And within the SRS resource set, you will have, for example, different or 1 or 2, 3 or 4 SRS resources, depending on the situation. I will explain this part in details. But under the SRS resource set, there is something called SRS resource. And this is like defining how the number of ports is going to be used by the SRS. So here, this will include the number of ports. So for example, assume that after the UE received this information, so he will understand that now he have 4 ports, for example, so he can transfer up to 4 sounding reference signal uplink using 4 different ports. For example, this is SRS1, 2 till port number n, for example. Then once the GMB receives this information, it will start estimating the uplink channel propagation and select the best SRS resource out of these 4, for example, different resources being submitted in the uplink here. So here the GMB is selected, and once it's selected the best information here, it needs to communicate back to the UE through the DCI information, which is downlink control information 01, to allocate the PU-SCH resources through including like multiple information. This information, the most important one called TPMI, which is transmit pre-coder matrix indication, telling him which one of the pre-coding matrix has been selected, and also something called SRI to tell him which one of these SRS resources is going to be used, for example, 1 or 2 or 3 or N, for example, and also other important information related to the rank. For example, the GNB will tell the user, based on the radio condition, based on the estimation, you are only capable to send only one layer, for example, only one data stream at a time. So the rank indication here, for example, is 1. Just telling him your rank will be 1. So now, and also it will give multiple other information such as number of resource flux is going to use for uplink PUCH in general, which is physical uplink shared channel. So once the UE received this information, now the UE is able to use the resource allocation received on the PDCCH to transmit the PUCH. Again, PDCCH is including the CI information 01, which has covered this information here. So then the UE will be able to transmit the PUCH in the uplink direction. This is how in general, the uplink beamforming is working based on the codebook-based, based on the sounding reference signal. Now I'd like to cover more details about, in general, what it means by transmit a pre-coding matrix or TPMI, what kind of entries, what is the maximum number of entries or pre-coding matrix can be defined by the standard, which is 3GPP, for example, what was, how many can be configured and so on, or in general standardized, which can be used by GNB to select any of these entities, and also what kind of configuration define the maximum number of TPMI can be used by the standard. So let's move forward, see what we have in details. Actually, this slide is just speaking again about the uplink beamforming codebook-based. Here I just would like to deliver two important key information. The first one related to the, in general, how the pre-coding matrix is identified by its TPMI. So for example, this is how, let me zoom in here. For example, here, as you can see, that first of all, there is a list of, as mentioned here, matrices where each matrix defines a set of pre-coding weights. And the dimension of these matrix depend on what? Two factors, actually. If you look into this figure here, the part here, highlighted here, they depend on the number of layers is going to be supported by the user, and also depend on the, and also identified by GNB, and also depend on the number of ports. This is actually number of ports is configured. You can instruct the user to use 1 or 2 or 3 or 4 ports based on also on his capability. For example, you can make it dynamic to reduce the number of ports from 2 to 1, depending on the vendor implementation. So the more the number of ports and the more the number of layers supported by the users and configured by the GNB, this can increase the number of pre-coding matrices or matrices, which can be used by GNB to select the best beam for the uplink transmission. So as you can see here, for example, the more the layers, the more number of ports, the larger the codebooks provide, and this is increase the benefits of increased flexibility. Increased flexibility because GNB will have more pre-coding matrix to select from, so it can find the best pre-coding matrix to maximize the signal to noise ratio for the PUCH. So for example, if I zoom in here again, assuming now this example for pre-coding matrix for 2 layers and 4 antenna ports, each like combination have number of entries, as I will explain shortly. For example, here it's assuming that you have 2 layers and 4 antenna ports. So for example, here we find that number of ports here is 0, 1. So here, since we have 4 rows, this means you have 4 ports. And the columns is 2. Since we have 2 layers, as mentioned here, this means you have 2 columns. So the first one here will be transmitted using 1 and 0. Like number of port 1, for example, antenna port 1, layer 1 will be transmitted through 1 and 0, as you can see here. So it will be transmitted. Then layer 1 again will be transmitted using 0 and 1, which is the second entry here, 0 and 1. Then the entry number 3 and 4 will be using -1 and 0, as you can see here, then 0 and -j. And this is actually using a different phase. I will explain this later on because this also different phase, it's required something called antenna coherency capability by the user. I'll explain this part. But the main outcome from here, I would like you to know about it, that the maximum number of TPMI depend on three main factors: the number of layers supported by the user, configured, and number of ports supported by the user, configured by GNB, and also depend on the UE capability for something called antenna coherency, as I will explain now. So, for example, here, as I mentioned, the bottom left table here, like summarizing the maximum number of TPMI entities or entries, where it can be used by GNB to select out of them. For example, here, for example, assuming that you have two antenna ports for antenna port scenarios. So here, assuming the maximum rank is 1. So if the antenna supporting something called fully and partial antenna and non-coherent antenna capability, this means supporting all different of capabilities. So you'll have maximum 6 entries. And with 2 rank, you have 3 entries. And if it's only supporting non-coherent, that this means it's not supporting any, like, it's not supporting the full coherency or full coherent. It supports only 2 entries. I will explain the coherent part because this is very important information. So if you look into here, the more we go higher ports and higher number of layers, the more the entries we will have, as you can see here. And also based on the capability, you will have more entries. For example, here you have 22 entries, while if for the same combination, if the antenna is not supporting full or partial coherent, non-coherent only, so the number of entries will be reducing. This means you have less or less number of codebooks. This means the benefit will reduce from the GNB side to select the best beam for the user in the uplink direction. Now, what it means by coherence, non-coherent. I have the next slide in more details about this part, but let me give you a high-level introduction before going into the details for this part. For example, if I zoom in here in the bottom right figure here, so this one, for example, I'm assuming that you have a codebook for layer 1 and 2 antenna ports. Then within this part, you have 6 entries. As you can see, 6 entries means 6 PMI, which can be, the GNB can select any of them. PMI 0, PMI 1, 2, or 3, or 4, or 5. So we have 6 entries, GNB can select that part. So based on what GNB would be selected? First of all, based on the UE capability. For example, assuming the user not supporting the coherence part. Coherence or non-coherence mean what? Coherence means that there's something called phase alignment. For example, the layer one, you have only one layer, can be transmitted through the 2 different ports. So if it's non-coherent, this means that the UE is not supporting the phase alignment, so it cannot send it in different phases. For example, usually if it's coherent, for example, it can transmit the same layers, for example, at phase 0, then at phase 90 degree, 270 or 180. This is means by coherence. So this is like if you can transmit the same signal using the 2 different ports, using different phase, this is increasing the number of entries. I'll also explain with more visual example in the next slide. So here's the first part here, assuming that you have one layer with 2 ports and the antenna of the UE is non-coherent. So in this case, you have 2 different entries, TPMI0 and TPMI1. In this case, the user cannot use both antenna ports at the same time. One of them should be inactive during the transmission. So the first part here, the layer 1 will be transmitted through antenna port 1, which is active. The second one will be inactive. That's why you find this 1 and 0. Then at the second time instance, the GNB, the UE will be transmitting the layer 1 again through antenna port 2, which is active, and antenna port 1 will be inactive, as you can see here. So it will transfer into 0 and 1. That's why it's non-coherent, so it cannot transmit both of them at the same time. While the coherence, if the user is supporting full coherence, this means the 2 ports is full coherence. This means that 2 ports can be used at the same time. Both of them can be active, but both of them will be transmitted at different phase. So to have this kind of differentiation between the same data stream. For example, layer 1 will be transmitted twice at this particular example, TPMI2, TPMI3. For example, here is using the 2 active antenna port, 1 and 2, and both of them, for example, using phase 0. Then both of them will be transmitted again, also will be both of them active at the same time. So they were using at this time, for example, let's say phase 90. So that's why I have 1 and minus 91. Then again, it will be adjustment to the phase by the UE for the TPMI4, for example, using phase 180, 2 active antenna ports. Then this one using 270. This means here the layer 1 or the data stream being transmitted from 2 different ports in 4 different directions, as an example, or 4 different phases. So this is increasing the entries where the GMB can select, having more chances or more flexibility to select any of those. This is kind of increasing or improving the UE beamforming capabilities. This is like as a short term here. If you find the user is not supporting the full coherence, this means the capability of the beamforming of the user is very less. So this can impact the beamforming capability of the user. Accordingly, it can impact the uplink performance. This is all about the meaning of the UE coherence. This information quoted from 5G NR in Bullet's book. You can refer to the book if you'd like to get more details, because you'll find in the book more information about different combinations. For example, 2 layers for antenna ports, 1 layer for ports, and so on. So you'll find all the combination if you'd like to go through. Now let's try to give you more examples about, in general, the meaning of antenna coherence, because it's very important to understand about it. Then I will be ending by how to check in general the related UE capabilities for the uplink beamforming and uplink transmission scheme in general, whether codebook or non-codebook and so on. So here I'm just trying to repeat the information about the antenna coherence. For example, I'm assuming there is 3 types actually of antenna coherence. Can be non-coherent antenna, coherent antenna, and even partial coherence or partial coherence antenna. UE, this is from the UE side. So for example, here in the non-coherence antenna, if I zoom in here, there is no phase alignment between data streams, okay? This means what? For example, assuming here 2 examples, I have 2 different 4 streams, 4 different streams, for example, for stream 1, stream 2, stream 3, stream 4 of data. Each one of these will be mapped to a single port. For example, this is port 0, port 1, port 3, port 4. So it will be having one-to-one mapping, so it cannot send like a different ports here. So each one will be mapped to a one-to-one mapping. So the UE will be able only to transmit the stream 1 through port 0, stream 2 through port 1, stream 3 through port 2, and so on, stream 4 through port 3. Okay, so there is like no phase alignment. So what it means by phase alignment, and what's the benefit out of this? For example, as I mentioned, the first benefit, it's increasing the number of entries, number of TPMI or pre-coding matrices, because you have more beams in different direction being sent whenever you have this kind of phase alignment. So for example, here non-coherence, it's having less number of entries, as you can see here, while full coherence is having all these kind of entries, the bottom down here. So why? Because for example, if I'm assuming this example, you have 4 different streams. So in terms of full coherence, what will happen? Stream 1 will be transmitted 4 times using the 4 ports, for example, at phase 0, phase 90, phase 180, phase 270. Then the same for stream 2, again will be transmitted 4 times through the different ports, and again stream 3 and stream 4 and so on. This will be the same. Also the same case for single layer, it will be transmitted 4 times through different 4 ports, but each will be using a different phase. So again, this is increasing the interest of the TPMI, so that GNB will have more flexibility to select the best beam in the uplink direction, so it can maximize the uplink user throughput. And in case of full coherence, actually, how the BTS will use the information. For example, the BTS know already, or can use its knowledge about the phase shift. It knows that this user already supporting full coherence, and it's has already a prior knowledge about the phase shift. It can help to combine the signal at the receiver side. At the GNB side, since it knows the phase shift, so it can combine the signal. Accordingly, this can be reflected in improving the signal to noise ratio. And again, this information quoted from 5G NR and Bollett's book, and also the next generation wireless access technology book. Here, actually, I would like to think loudly about from the practical perspective. For example, whenever you are speaking about uplink codebook transmission, what kind of consideration and requirement you need to understand whenever you are trying, for example, to improve the uplink performance, or even based on your vendor implementation or whatever. So I would like first to cover 3 important aspects here. The first one, in general, you need to understand that the number of ports equate to the number of layers. What it means by this? Assume the user supporting maximum 4 ports. This means the user can support maximum up to 4 layers. So in case if the GMB decided to assign 4 layers to the user, let's say rank 4, so in this case, the GMB as well must, from the very beginning, assign 4 ports. So for example, assume you have a manual configuration and you reduce the number of ports to 2 or 1. This means you will be reducing the number of data stream or rank. So in summary, the more ports you have, the higher the rank you can get if you have a good quality or good SNR. This can be dynamic change done based on the vendor implementation. For example, the GMB can decide to reduce or increase the number of ports based on the SNR. But other important information is very important. The more antenna ports configured, this means each port or each antenna transmission using the port, different port, will have less power. Assume you have now the full UE power using only one port. All the power will be only used by one port. So this will be like a much better coverage for this particular port. Assume you increase it to 2 ports. In this case, you will have around 3 dB less or loss and with each antenna port. The total power itself, which will be remain the same, it's called total power unity. However, the power per port will be less. So this can impact your coverage, right? So for example, assuming in the right side here, assuming you are in the very same edge here at this example, and you decided to make it 2 ports, or the GMB decided to assign 2 ports. This means each of these ports will have a less coverage. This means this will be impacting your SRS and the uplink transmission. Accordingly, it will be reflecting in many different things, including uplink data transfer, which is PUSCH, and sometimes also can impact the downlink performance, because at the end, sometimes the SRS is using the channel reciprocity to estimate the downlink channel propagation. So if you reduce the coverage here, this might be a problem for the devices and also for the performance in terms of uplink and downlink. So other consideration you need to know, which we just discussed, it's about the antenna ports coherency capability. For example, we assume that antenna coherent, or if the antenna is coherent or supporting the full coherency or full coherent, this means the performance or the beamforming capability is much higher. So the beamforming here in this case can compensate, for example, the power reduction here. For example, assuming here you have 1 port or 2 ports, but the user is supporting or the device supporting antenna coherence, this can kind of improve the performance because you have more entries of the PMI report. And the opposite way around, if you don't, the UE is not supporting the antenna coherence, it's non-coherent as mentioned here. This means in this case you should ensure that the very edge users only configure those 1 port to ensure that he's getting the full power per port. If you increase the number of ports, so this means you will have less power per port, and at the same time the UE himself is not supporting antenna coherency, so this will impact the coverage for this particular user. So again, as we highlighted before, more ports and layers, means larger code box, means you have more flexibility for the GMB to select more TPMI reports, so it can increase the flexibility and improve the beamforming. But at the same time, there is other drawbacks associated here, which is related to that the more code box you have, this means you will have a larger overhead due to the TPMI report itself, which will be larger. So this can reflect, for example, in the overhead, especially whenever the GMB is sending the feedback in the PDCCH in the downlink direction. The second part here, it's about the GMB schedule capability itself. For example, this will depend on different, again, vendors, implementation, and so on. But the main consideration GMB usually should consider is the matching between the UE capability and the channel condition. UE capability, this is like how many ports is being supported, how many layers, the antenna coherency itself, like the UE supporting antenna coherent, non-coherent. So for example, in this particular example on the right side here, let me zoom in. In this particular example, I'm assuming that the green area, the quality and coverage of the SRS is very good. So since the quality and coverage is very good here for the SRS, so the GMB can rely on the SRS to estimate the uplink data. So for example, here it can assign that for this user that please use 2 ports, and also the rank is 2 layers. So in this case, you will not be very worry about reducing the coverage here, because already the user have a good signal to noise ratio and quality. So if the schedule is being able to identify how many ports, for example, to be assigned here and layers based on the radio condition, this can maximize the benefit. For example, in this particular case, the more the layers, it will maximize your throughput. For example, you have 2 layers, you can even double the throughput compared to 1 layer. But in case, for example, in the very edge here, if you give the same condition to the user, for example, you give him 2 ports and 2 layers, you are trying to maximize the throughput for the users, but the user is not capable to send any feedback and uplink because of the limitation of the coverage. So in this case, the GNB need to decide based on the quality, for example, SNR, if it's dynamic or if it's manual to configure only 1 port or whatever for a particular users. Here, for example, GNB will decide that this particular user can only use 1 port and only 1 layer. Okay, and in other case, if it's in the middle coverage, for example, it can decide, and for example, supporting the antenna coherent, full coherent. So in this case, can use, for example, 2 TX port and 1 layer. Why? Because the more ports, as I mentioned before, increasing the PMI or pre-coding matrix entries. So increasing the pre-coding matrix entries, also increasing the probability to have more entries. So the GNB will have more flexibility to select the best PMI report to send it to the UE in the downlink direction, so the user can know what is the best beam to use in the uplink direction, which is related to the PUCH transmission. So this is again based on the GNB scheduler. It should be capable of matching the capability and the channel conditions. For example, use fewer ports for cell edge to maximize the coverage at this example, or use more layer ports for high SI-R signal to noise ratio users to maximize the throughput, as highlighted in the green example. The last part actually also is a capability that whenever the GNB will decide to use the DMRS instead of SRS. Okay, let me zoom into this visual example, which is quoted from 5G NR in Bollett's book. As you can see here in this example, the first thing I would like to know, a very important information, that initial rank in the selection, the maximum rank selection for the user will be decided based on SRS. The maximum rank is only decided based on SRS, sounding reference signal. For example, as you can see in this example, the GNB decided based on the transmission for 4 SRS resources to assign rank 4 for the user, which is the maximum rank in this case because the user is supporting 4 layers and 4 ports. So since the GNB decided to assign the maximum rank here based on the SRS feedback in the uplink direction and the estimation from GNB, so in this case, since already the user is transmitting with the maximum number of layers, and whenever the GNB assign the PUCH resources, it also use the DMRS in the same time. You will have all the time the DMRS, as you know, will be associated with the PUCH. So in this case, since you have the maximum rank already being used, so now the uplink channel propagation, the GNB can use the DMRS instead of SRS. And why it will do this? To reduce the overhead overhead of the SRS, so it can maximize the maximum user throughput to use the DMRS to estimate, for example, the rank and so on. So here, the complete information can be derived from DMRS because you have rank 4 here, which is a maximum rank. So no requirement at this stage for the sounding reference signal. But based on the DMRS feedback, the GNB can decide, in this case, to reduce the number of rank. Assume that the quality of the DMRS reduced, so GNB found out that the user cannot have rank 4 anymore. So it should use, for example, rank 1 as this example. So GNB decided to reduce the rank from rank 4 to rank 1. PUCH, and already the DMRS recoded will be associated with the PUCH. But in this case, since the maximum transmission and the uplink is not being used anymore, so DMRS cannot be used anymore for the estimation for uplink channel propagation. Why? Because, for example, if the GNB decided again to increase the rank, it needs to know all the information about all the for example, transmission from the user side, for example, over the SRS resources. So it needs to switch back to SRS. So, for example, here it will again start measuring all the SRS transmission at different number of ports. So, for example, if the user moved again to a good radio condition, it can increase the rank again. So, as just a high-level summary for this part here, the maximum rank is defined based on SRS. Rank tuning can be done based on DMRS or SRS. And when I say rank tuning, means rank reduction from the maximum to, for example, to lower numbers. But the maximum always based on the SRS. So this is actually the main consideration for the Uplink codebook. Now let's move forward to the UE capability check, how to check all the related capabilities for the UE for the Uplink beam. So in this slide, actually, 3GPP actually highlighted there is multiple UE capabilities for the uplink need to be checked. For example, here in the left figure here, I'm highlighting under the feature setup uplink. You will find after the feature set uplink per CC, you will have multiple configurations related to the MIMO codebook PUSCH codebook. Here, actually, this is CV. You can also find the same information for non-codebook. Under the codebook PUSCH, you'll find that it's having different information here. The first one related to the maximum number of MIMO layers for the codebook PUSCH. For example, here 2 layers. And here, this is the maximum number of SRS resource set. For example, assume the user supporting 2 antenna panels. So this means he can support up to 2 SRS resources in this case. Also, the modulation, for example, here, this is 256 QAM in the uplink, the uplink direction. And also, there is other information related to MIMO non-codebook PUSCH. This will be mainly including the maximum number of layers supported by the non-codebook PUSCH. The second piece of information, which is very, very important as well, it's related to the capability of the device of the transmission coherence. For example, here it's assuming as non-coherent. This means there is independent, there is no phase alignment. This means this can be used only for the basic MIMO, but the beamforming capability would be much less. Assuming this one is coherence or coherent, full coherent as mentioned here. So in this case, this means it having a phase alignment, and this is supporting advanced beamforming, so this can increase or even improving the uplink coverage for this particular user. So, for example, you can do insight in your network to check the capabilities for the devices in the network to find out with how many devices supporting the antenna coherent and non-coherent, antenna full coherent, non-coherent, or even partial coherent. And the partial coherent or partial coherent, this is only for the 4 ports supported capable user. For 1 and 2 ports, this is only can support even full coherent or non-coherent. So you can do insight just to check the capability in your network to understand what kind of tuning you need to do. For example, you can do a specific tuning for the devices supporting the full coherent. For example, give more ports to increase the number of TPMI reports, and the opposite way around for the non-coherent devices, just to assign 1 port to improve the uplink coverage, because this port means you will have more power per port, which is 1 port, for example. The second type of the uplink beamforming, or in other words, the uplink transmission scheme, is related to the non-codebook based, right? Actually, non-codebook based, this is again based on the channel reciprocity. This is the same concept as we highlighted in the previous session. For example, whenever the channel reciprocity is there for downlink beam management, the SRS, which is the transmission uplink, can be used to estimate the downlink channel propagation. Now it's the opposite way around. Now the downlink transmission can be used to estimate the uplink channel propagation based on the channel reciprocity. As we highlighted, this is mainly for the TDD, time division duplex, because TDD is using the same frequency in uplink and downlink, but just the transmission is happening in different time in the frame. So how the procedures for non-codebook based transmission is triggered or working. Initially, as we highlighted in the previous one as well, for the codebook based, that initially the GMB need to know the UE capability. So the first information in the very beginning would be transferred from the UE to GMB, telling them, for example, I'm supporting codebook based or non-codebook based, and this is the maximum number of layers I'm supporting in terms of non-codebook based, for example, 2 layers and so on. So once the GMB know the capability, it will check, for example, if it's assumed there is a channel reciprocity and non-codebook is suitable for the user to be used in this case. So it will be sending the RRCU confirmation message and this RRT will have SRS resource set. Usage will be set to usage will be set to non-codebook, and under this SRS resource set, it will include the number of something called SRS resources, which can be configured with a single port up to 4. For example, within this one, the SRS resource can have 1 or 2 or 3 or 4 ports, for example. And based on these 4 ports, since the UE will now estimate the uplink channel propagation based on the CSI-RS, it can now send directly a pre-coded SRS, for example, for each different port, for example, port 1, 2, 3, sending for pre-coded SRS, and the GMB will be selecting one of these 4, select the best or select the pre-coded beams out of these, and then GMB, after selecting the pre-coder beams, it will be sending back and assigning the related resources for the PU SCCH for the uplink transmission, data transmission, which is including will be sent through a PDCCH channel, which is DCI format 01, which will be including the SRI, and this SRI, which is SRS resource indication, telling, for example, I would like to use this pre-coded SRS3. So UE will understand, he will start or transmitting the PUCH and its DMRS using this specified SRI or SRS resources. So this is again based on the code non-code block, which is again during the channel reciprocity. And as I highlighted, this is only supported by the TDD. And the last part in today's session, it's about the uplink beam management in general. For example, if the user is transmitting different beams in the uplink and the GMB need to select the best beam for the user in the uplink transmission, and also the best beam in terms of the GMB side as a best receive uplink beam, how this can be done. First of all, as highlighted here, the uplink beam management is not required or necessary whenever there is something called uplink downlink beam correspondence capability. If it's supported by the user, this means the uplink beam management is not required at all. What it means by uplink beam management capability? Actually, this means that whenever the user is supporting the beam correspondence, as mentioned here in this capability message on the right side here, if this is being supported, this means that the beam which is already selected for downlink transmission can be used for uplink. The best beams in downlink direction can also be used or assumed to be the best beam in uplink direction. That's why it's called beam correspondence. And the opposite way around, the best beams in uplink direction can be used also for downlink. So in case if the beam correspondence capability is supported by the user, there is no need for uplink beam management at all. Okay. However, in case if it's not supported, in this case, the SRS can be used for uplink beam management. In case of the uplink beam correspondence is not being supported, then the SRS can be used by the GMP to select the best beam in uplink. So what it means by this and how it's being working in 5G in general. Just as from high level perspective, actually the fundamental procedures involved is that the UE transmitting the SRS in each beam position as shown here, different position. I'll explain the technical details here, but just the fundamental procedures. So the UE transmitting the SRS in each beam position, which allow the BTS to select the best UE transmitting beam out of these 4, for example, and also the best BTS receive beam, which is information the GMB does not require to transfer to the user for the best BTS receive beam, but it needs to transfer what is the best UE transmit beam. So how this all is being working? So for example, this example, the bottom down here example, assuming that we have the capability of the device supporting only one antenna panel. Sometimes you find 2 antenna panels. So here I'm just assuming there is 1 antenna panel, okay? And has the 1 antenna panel has 2 polarization, as you can see here, with a separate antenna port. For example, you have a port 1 plus 45, then another polarization with port 2 minus 45. And actually, the GMB in this case assigned 4 different SRS resources within the SRS resource set. So initially, the procedure is like the following. First of all, the SRS resource set will be 1 because you have only 1 antenna panel, and the usage will be set to beam management. If you remember in the previous 2 cases, you have codebook and non-codebook. But since the SRS this time will be used for the beam management, so the SRS resource set usage should be beam management. And because the GMB would like the user to transfer or to transmit the beams in 4 different positions, as shown here, so it will configure the user with 4 SRS resource within the SRS resource set. So we'll find under this one 4 SRS resources: SRS resource 1, 2, 3, and 4. And each of these SRS resources will have a separate configuration. For example, first of all, the number of ports here assumed to be 2, so all of them will have a 2 ports configuration. But again, the start position and the phase and these kind of things will be different from one to another, and also the timing to be able to generate this different beams in different directions as shown here. For example, the first beam was transmitted in this direction using 2 ports, then it changed the direction, and again and again and again, as you can see here. But the most important part as well, that GMB must assign a unique SRS resource identity for those to ensure the feedback later on from the BTS is not ambiguous when the GMB or the BTS signal back the best beam for a selected beam out of this 4. For example, each one will have a unique identity. So, for example, the GMB would like to tell the user, I would like you to use in the future transmission, uplink transmission for PUSCH, for example, SRS resource 1 or 4. So that's why it needs to have a unique identity for each of them. So whenever the GMB signal back the identity of the best beam, the UE will understand which one is being selected. And again, as I highlighted, how the UE will transferring this one in different timing. This is actually all configured by the GMB to the user within each of the SRS resource. This like configured with different timing and resource mapping using this called start position. If you look into the configuration, you find all this information. So as a summary here, once the GMB or BTS has identified the best UE transmit beams, then it must signal the identity of the relevant SRS resources to the user or to the UE, and this allows the UE to use the best beams for the future transmission. Future transmission means PUSCH transmission in the future. And this actually was the last part of today's video. I hope if you like the session and to share it and spread the words and press like and also drop a comments with any questions or even any requirements in the near future. Thank you very much and see you in the next video.